Okay, so last time, what did we do? We did limits. We did limits of vector valued functions, and after the intro to vector valued functions, so you got a chance to do your limits. And so here's some limits means for you. I like this one. That's wonderful. And then this one is just crazy fun. After explaining this to my students several times, the limit as x approaches 8 of 1 over x minus 8 is infinity, which is true, 1 over 0 infinity. I want to check if she really understood it and gave her another example. And this was the result. Limit as x approaches 5 of 1 over x minus 5 is, and then the student put a 5 sideways. You got to love that, okay? You got to look for the comedy somewhere. Okay, so let's do differentiation and integration of vector valued functions, shall we? So what about it? Well, we're finally hitting more calculus. Did a little bit last week with limits of vector valued functions. Now we're going to do some more calculus on vector valued functions. We'll differentiate and integrate, okay? So the definition of derivative looks almost exactly like the definition of derivative that you had back in Calculus 1. Really? Yeah, check this out. It's the limit definition for a derivative. Oh, yeah. So you've got your vector value function r, and when you do r prime, you take the limit as delta t goes to 0 of r of t plus delta t minus r of t over delta t. This quotient right here is called the difference quotient, and it's very important. You see that a lot in calculus. And of course, this derivative is wonderful provided the limit exists. And if the limit exists, we say that r is differentiable at t. And if it exists for all t, then it's completely differentiable on the entire interval. Now, we're going to run into vector valued functions that are, for the most part, differentiable on most of the number line. There may be some points that they aren't differentiable, and we'll take a look at that. So the idea is, and I want to show you this component by component basis, here's your vector valued function, either written as a linear combination of the standard unit vectors, or my personal favorite, component form right here. So if somebody says, go find r prime, and you use this limit definition, how do you do that? So I'm going to do this in slow motion because I think it's worthwhile for you to see. If you take the limit as delta t goes to 0 of the function itself, but evaluated at t plus delta t. So you're going to have f of t plus delta t times I, or I hat, plus g of t plus delta t times j hat. So there's that guy right there, minus, and I'll even change colors to make a point, the original vector valued function. So f of t I hat plus g of t j hat there. And that's all over delta t. And we're taking a limit as delta t goes to 0. So then what? Well, I'm just going to rearrange the numerator a little bit. So how am I going to rearrange it? I'm going to distribute this negative and then put the f terms next to each other like this. In fact, what I'll do like this, let me do this, right? Just pull this out. I hat like that, much nicer. And then I'll collect the G terms like this. Then what? Well, what you're supposed to notice is that this right here, this limit, is the definition of derivative that you had from Calculus 1. So this is really, so you're taking this limit here. So if you distribute this limit, this right here is just f prime of t times I hat, like that. Plus, and then when you distribute the limit from that guy is just g prime of t. Okay, so why do you care? Because it's really, really, really easy to do a derivative of a vector valued function. So all you have to know, essentially, if somebody says, hey, go find r prime, is you individually take the derivative of each of the components. That's all. It's that easy. And for a 3D version, no problem. Just extend it. Take the derivative of the first component, second component, and the third component. So that's how fun and easy it is. But the question is, are you hopefully memorizing all of your derivative formulas, because that's important. Okay, so you can see that from this figure down here that r prime is also a vector valued function itself from this definition. And also you can see that how they find it is here's r of t, here's r of t plus a little extra, you know, where you increase t by a little bit. And what you're doing is you're saying delta t is going down to 0. So this vector here is going to go that way. It's going to get squeezed like this until it finally, you get r of t plus delta t minus r of t, which you remember when I told you about subtraction? Subtraction connects the tips. Oops, I need a different color. It connects the tips of two vectors. So it's connecting the tip of r of t to r of t plus delta t. So when this vector here starts moving in that direction, you eventually get r prime of t vector. We're going to talk about this geometrically speaking right now, and this is the key fact I want you to know. From this figure, r prime is a vector, it's a vector valued function, that's tangent to the curve given by r of t and pointing in the direction of increasing t values. Now, why do you care about this? Because look, when you took calculus 1 and somebody said, hey, here's a point, would you please go find the equation of the tangent line to that point, like this? Remember this? And you remember that the slope of this tangent line was what? Anybody remember this? Okay, I'm going to call on somebody.
Wasn't it the derivative of the graph at that point, or of
Yes.
the?
Thank you, Sebastian. That's right. F prime of C. That's the slope. So when you're finding the slope of a tangent line back in Calc 1 to the graph of a function, the slope is F prime. Okay, fine. Well, in the world of vector valued functions, we still sort of have that concept, although we're not going to talk about slope. Here's your graph of your vector valued function, the original one, right there. And let's say right here at this point, right at that point, when let's say t is equal to some number, like a seconds, right there at that point, the r prime of a is a vector that's tangent to the curve. That's key right here. And if you don't get that, well, then, you know, one of the problems on this week's midterm coming up on Monday might be a little bit of a problem. So today's material will be on the midterm, by the way, the exam coming up on Monday. So you definitely want to keep a heads up on that, today's stuff. Okay, let's continue. Let's find some derivatives. And I'm going to start with an easy one, and then we'll get harder and harder. So take a look at this vector valued function, and okay, got some components there. What would r prime of t equal? That's the question. The good news is it's also going to be a vector valued function. And in other words, it's going to have 3 components, and our job is to find all 3. So I like to do this piecemeal. So what I do is I take each component in turn. So I go, what is the derivative with respect to t of the first component? And I like to rewrite 1 over t as t to the -1, and then using the power rule. And then I don't like negative exponents. So there's your first derivative. Yay. And then the second component, we're going to take his derivative. And you know the derivative for a logarithm is 1 over u, or 1 over 2 minus t, times the derivative of 2 minus t, which is -1. We can clean this up a little bit like that. And then finally, what is the derivative of cos 3 pi t? And I think that's going to be a negative sign. And then not only negative sign, but you also want to multiply the sign by the derivative of 3 pi t, which is 3 pi, using the chain rule. So your final answer, you're going to want to put your r prime into component form. So here I go. R prime of t is going to equal -1 over t squared, comma, -1 over 2 minus t, comma, -3 pi sine 3 pi t. And I'm done. I just found the derivative of a vector valued function. Success! Yay! Questions so far? Everybody
The 2t
okay?
is t squared.
Negative 1 over t squared.
Oh, okay. Sorry.
Negative 1 over t squared is the first component. Does that answer your question or?
Yeah, that does.
Okay. Okay. So now let's go ahead on something tougher. And usually I give tougher derivatives. I expect that people know how to do all the stuff that they learned in Calc 1 and Calc 2, chain rule and all that good stuff. So let's take a look at cos cubed of 2t. What I like to do before I take the derivative of a trig function getting raised to a power is rewrite it. So that way I can see the chain rule has to happen. So first, using the power rule, I'm going to take the derivative cos 2t square, 2t cubed is going to be 3 times the cos raised to the second power, and then chain rule times the derivative of cos 2t, which is going to be negative 2 sine 2t. Clean this up, otherwise I will not give you full credit. What do I mean by cleanup? Please multiply the 3 and the negative 2, which is negative 6, and put your coefficients in front. Then you've got your cos squared 2t multiplied with your sine of 2t. And so we're done taking the derivative of the first component. Now, the second component, a lot of people don't remember their log properties, so they get into a world of hurt. Let me show you how to start this, how I don't want you to do it, okay? So how I don't want you to do taking the derivative of that logarithm with that nasty argument is I don't want you to immediately start trying to take its derivative. Like you don't want to go like, okay, ln of this horrible thing, okay, 1 over that horrible thing times the derivative of the horrible. You're just going to end up in a world of hurt. And I'm not even going to give you full credit anyway. Even if you get lucky enough to finally get the right answer, I'm going to take points away from you for wasting time. Yeah. Yeah. You should know how to do things elegantly. Well, what do you mean? Well, look, don't take a derivative yet. Use some log properties to completely expand and simplify that logarithm. And then once it's expanded, take your derivative term by term. So the 3 log properties that you should know of, and I'm just doing a reminder right here. Ln of A times B is ln of A plus ln of B. That's how you expand it. Ln of a quotient is the difference of logs. And if you have an argument raised to a power, the power can sneak out in front and become a coefficient. And be careful, here's what's not true. If you have ln of A, the entire thing raised to an nth, that is not equal to n ln of A. Okay, please don't. So what am I saying? If I look at this 5th root, which is pretty god awful, the first thing I'm going to do is rewrite the 5th root with a rational exponent, which is to the 1/5 power. Then I can simplify the log by pulling the 1/5 out in front, and I'm not done. I'm going to continue to simplify this. I'm going to put an error in here. See if you can't find it. What did I do wrong here? There's a slight error. Does anybody see it?
You missed the 1/5 on the second.
Good. The 1/5 has to be distributed. Thank you. And now, can I go any further, or is this completely simplified? So my question to you is this true or false? Is ln of A plus B equal to ln of A plus ln of B? And if it's true, then I can keep expanding, yeah? True or false?
That's false, right?
Good, that's false. Do not take a sum as the argument and break it out. That's not even true, not even close. So we're done here. Now what? Well, now you can take the derivative of this, and it's going to be so much nicer and easier than try to take that derivative of that original log. It is equivalent, pretty much. So now you can use your knowledge of taking derivatives of logs. So this is going to be, 1/5 times 1 over 6t plus 1 times the derivative of 6t plus 1, which is 6, minus 1/5 1 over t squared plus 2 times the derivative of t squared plus 2. And then we can clean this up a little bit and simply, and by the way, on the bottom, don't distribute the 5. Please don't. I know some of you want to do that. Don't. It looks better factored. Okay, so there, we took the derivative of the second component, and now I'm ready to go to the last component, 9t squared e to the negative 2t, and take that component's derivative. Now, when you're taking the derivative of this guy, you need to use the product rule. And I'm really a big fan of the product rule, as we'll see today. So remember that if you're being asked to, this is just from Calc 1, if you have a product f times g, somebody says d dx, that's f prime g plus g prime f. Okay, just a little reminder there. So if I call this factor f and this factor g, then this is going to give me f prime g plus g prime f. So f prime would be the derivative of 9t squared, which is 18t, times g, that's the exponential, e to the negative 2t, plus g prime, that's the derivative of e to the negative 2t, which is negative 2 e to the negative 2t, times your original f, which is 9t squared. Clean this up. I want the 9 and the negative 2 multiplied, and I like polynomial coefficients to go in front of exponentials and trig, just to make it look prettier. You can factor out a common factor, but I'm not going to, just because I don't feel like it, although you can, and I'm okay with it. Okay, so final answer for this problem. You got your derivative r prime, and you're going to have the negative 6 cos squared 2t sine of 2t. That's your first component. Second component was 6 over 5, 2t plus 1 minus 2t all over 5 times t squared plus 2. And don't bother trying to find a common denominator for those two terms. I don't require that you try and rewrite that as a single quotient. Just skip it. And then finally, the last thing we did there, which was the product rule. And we're done with this. Wow, that took a while. That was nuts. Okay. So there is the derivative of a vector valued function. Questions?
It says product rule, right?
Yes.
Okay. Just making sure.
Okay, so moving up to the, so that was that one. Do I have another one in here somewhere? Letter C. Oh, I'm not going to do letter C. I'll let you do it. Okay. I do want to say that on this one, you're going to need the quotient rule. Okay. And just a quick review. How do you take the derivative of arctan? And hopefully you remember how to do this. The derivative of arctan of u is u prime all over 1 plus u squared. So I'll let you figure that out. If I were you, I would expand this logarithm first before taking the derivative. And on the last component, use that wonderful chain rule. Okay, so know how to do all of these for my quizzes and exams. And big old exam 1 is coming up. That's going to be on Monday. Looking forward to it. So I think everybody's here right now. Is that right? Maybe not. I think we might be missing somebody today. Maybe they're taking the day off for George Washington's birthday. I don't know. But I do want to say, when you are Zooming next week on your exam with your phone, the phone has to be placed like on a shelf, like over to your left, so I can see you, your workspace, and your screen. And you'll check in by putting your photo ID next to your face, like, hey, cheese. And I need to tell that it's really you with the photo ID and your name. Okay. If your Zoom drops out on your phone at any time during the exam, and I'm proctoring, so I'm going to go into a private breakout room that you're in and see you, I will email you and say, hey, your Zoom's down. And so you need to put something on your phone that gives you, some sort of notification that you've got an email from me, because I'll be saying, hey, your Zoom isn't, it's something happened. And so you need to resume. Make sure that you keep kind of apprised of that, because if you don't, and I come in there and you don't answer your email, I will stop your exam. In other words, I'll go into my math lab and then cut you off, okay? You don't want that to happen, so please be aware. And this is all to maintain integrity of the exams. I've had a lot of issues with that. All right, let's move on. Let's do some more derivatives. So what if somebody said, hey, take the derivative of a dot product of two vector valued functions or something weird like that? How would you do that? So that's what this theorem addresses, all sorts of different combinations of using vector valued functions where they'd show up. And how do you take the derivative of it? Now some of it's like obvious, like Captain Obvious would be number one here. Oh, what if you had some scalar multiple of your vector valued function? No problem. The derivative is just going to be the scalar multiple times the derivative. Okay, that's straightforward. Number two is pretty straightforward. If you have a sum or difference of two different vector valued functions and somebody says, hey, go take the derivative. No problem. Take the derivatives individually and then simply add or subtract it. And then you'll get one big old vector valued function. This one is interesting because it's not a dot product. This is a scalar function. What the heck is a scalar function? It's not a vector valued function. W wouldn't have a vector on it. It would just be like, I'm just making something up. A scalar function would be like, I don't know, t squared sine of 2t or something like that. It's not a vector valued function. Whereas r of t would be a vector valued function. Remember, that's very different. That would look like, I'm just coming up with some weird thing, you know, t, I'm just making something up, ln of t, 1 over t minus 1 or something like that. What if you were multiplying a scalar function with a vector valued function? And they said, take the derivative. You would use the product rule. See the product rule in action there? So you'd have your scalar function times the derivative of r prime plus the derivative of your scalar function times r of t. Okay, now this is a dot product right here. That is a legit dot product because you're multiplying a vector valued function with a vector valued function. So you would just use the dot product. So there's two ways to do that problem. One, first do the dot product and then just take the derivative of each of those resultant components. Well, it's going to be a scalar function. This is the result is a scalar function because you're going to take a dot product of two vector valued functions and then take the derivative of that, or you could use the product rule. So this is what I love because the product rule just keeps showing up and showing up and showing up, which is kind of great. So there's the product rule in action again. I love the product rule. I'm super into the product rule, by the way. That's a big hint. And I am when I teach Calc 2 also. I even tell them, I love that product rule. It's going to show up like in all your future math classes. So you should do it. Here's another one. What if you were taking a cross product of two vector valued functions, assuming, of course, they're both 3D? Then you're going to use the product rule. And by the way, these are dots in between. I forgot to tell you, those are dot products right there. Dot product of those. So you're going to use cross product with the product rule. Cross product and the product rule together. Product rule again. Okay, now what if you have a composite function? So you have r of w of t. You use the chain rule and you take r prime of wt and multiply it with w prime. Fine. Now this one I have a little arrow by because it's really weird and I'm going to prove it. It's not intuitive. If you take the dot product of a vector valued function with itself and it gives you a constant, just a pure number like 5 or something like that, it turns out that this is true, that the dot product of the original vector valued function with his own personal derivative is 0. Now, what does it mean when the dot product of two vectors is equal to 0? What can we say about the relationship between those two guys?
They're orthogonal.
Yes, very good. They're orthogonal. Nice. I'm going to prove number 7. It's a real quick and dirty proof. So let's say you're given that r dot product with itself is a constant. This is true. You get that for free. Then what? Can I prove that r dot with r prime is 0? Check this out. I'm going to take the derivative of both sides of this equation with respect to time t. And let's do the right-hand side first because it's easy. what you guys know this from Calc 1. What is the derivative of a pure number?
Nothing.
0.
0. Yeah, like what's the derivative of 2? 0. Okay, so on the left-hand side, we're going to use the product rule because we're going to basically use number 4 from the theorem up above, that when you take the derivative, just scroll up here, oops, my erase tool isn't working. When you take the derivative of a dot product of two vectors, you have to use the product rule. So here it's the dot product of a vector with itself, but no problem. I'm going to use the product rule, r dot product with r prime plus r prime dot product with r equals 0. But these are like terms, so you can add them together. 1 apple plus 1 apple is 2 apples. So you have 2 of these r dot product with r prime equals 0. And then I'm going to just simply divide both sides of the equation by 2, and that gives me the result. And so there you go, end of proof. And it's true that now the dot product of the vector valued function with its derivative will be 0. And that means that there's an orthogonal relationship between the vector valued function and its derivative. Okay, so we're done there. Let's do one more of these, and then we'll move on to do some integration, which is the hard part. So what if somebody did give you a vector valued function and another one and said, go take the derivative of the dot product? Okay, so you could do the dot product first, then differentiate, but let's go ahead and use the theorem above there, which says that it's going to be the product rule in action. Okay, so I'm going to just do that. And so let's get the r prime and the u prime, and then we'll put it into this product rule. So what is r prime? So if you look at these 3 components, I'm just going to differentiate on a component by component basis. The derivative of 1 over t, I think we already did that one. It ended up being negative 1 over t squared. The derivative of negative 1 is 0, and the derivative of ln of t is 1 over t. Okay. The u prime is easy because u is just got some polynomial components. So the derivative of the first component, t squared, is 2t. The derivative of the second component is just negative 2, and the derivative of 1 is 0. Okay, so now when I'm finding the derivative of the dot product of these two guys, I'm just going to use this product rule here. So first it's going to be r prime, and these are dot, I have to put dot products in between. It's going to be r prime dot product with the original u. And I'm using component form just because I think it's cleaner. And then plus, and then I'm going to take the dot product of the vector valued function r, which is 1 over t, 1 ln of t, and dot product that with u prime, which we just got, 2t negative 2, 0. And then just use my knowledge of dot product. So for this first dot product, I'll have negative 1 over t squared times t squared plus, well, 0 times anything is 0, plus 1 over t times 1. And then for the next dot product, I'll have 1 over t times 2t plus 1 times negative 2 plus ln of t times 0. Okay, that's just going to be 0. And then if I clean this mess up, I'm going to get a scalar function. Let's see, this reduces to negative 1. Oh, that's really nice. What else do we have here? Let's see, plus this is 1 over t, plus this one reduces to 2. And then this one is minus 2. And this is not adding up. What the heck is happening here? Did I do something wrong? U prime with r. That's my problem right here. U prime, here's U prime with r. Did I copy something down wrong? That's 2. Oh, I think I did copy down something wrong. This r has a negative 1. Ah, they tried to trick me. Aha! You see that's a negative 1 component? Yeah. So that's really a plus 2. Aha. So that is going to give me, well, I have -1 plus 4. That will give me the 3. And then plus 1 over t. So this is a scalar function. It's not a vector valued function. So forgetting a negative can really mess you up. Okay, and here's the fun meme I have here. I found this comic about a year ago. I just thought it was really cute. In the second semester, we'll be touching on parametric derivative formulas, which is what we're doing right now. Oh man. And then the teacher looks at the student and he smiles. Today, I'll explain what parametric derivative formulas are. Oh man. Okay. Here's another meme. The fundamental theorem of calculus tattooed on that guy's back. Okay, why do we need that? It's a good segue into what we're just about to do. We're going to take integrals of vector valued functions now. Congratulations. Let's do an integral. Good news and bad news. The good news is that when you take an integral of a vector valued function, it's really similar to just doing integrals from Calc 1 and Calc 2. You just integrate. Then what's the hard part? Well, the hard part is you have to remember your plus c, but your plus c, you have to do 3 separate times or 2, depending on your dimension of your vector valued function. And you basically collect all those into a constant vector. Okay, so that's the key. So let's look at this official definition here, which I claim is lacking, and we'll give the missing part. So if somebody says, hey, integrate a vector valued function, you're like, oh my goodness, can I even do that? Yes, you're going to get a vector valued function, and all you have to do is integrate each of the components separately. And the same thing for 3D here. Boom, 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 for space, 3D. Now, what if you have a definite integral? Same kind of thing. You'll just integrate each of the components separately, using your knowledge of definite integrals. And you'll need the fundamental theorem of calculus, of course, which is right there, that when you finally get your antiderivative, don't forget to evaluate at the upper limit minus the lower limit. Okay, now what's missing? From these indefinite integrals here, these are the indefinite ones, you're missing the constant of integration. So when you integrate a vector valued function, let's just do the 2D version because it's easier. You're going to get an antiderivative plus some constant. We'll call it C1. And with the second component, you'll get some antiderivative plus C2. So you have to remember that. Another way you can write this is you could combine the constants into its own vector and then simply rename it. So this is a legal answer right here, but you have to be careful. This is a constant vector. I'll just call it C and then use vector notation. It's not a pure number constant. So I will require, if you are going to do it this way, to put the little vector on its head. So we all know, using the correct notation, that it's a constant vector, not just a single number sitting out there hanging out. Okay, so now we're just going to do a whole bunch of integration. Okay, and I'm going to give you a shot to do one. What the heck? Let's see here. And then we got to do velocity and acceleration, right? Ooh, yeah. Yeah. So what is on the agenda for this week before I go ahead and do all this? Nope, that's not what I was looking for. I thought we had the syllabus here. Nope. Let's go back into syllabus. So I hope that you're keeping track of where we are and what we're doing, because the syllabus is your guide to how the course is rolling out. And so the calendar in there is the key part. If it shows up, it's taking time to load. So if you go down here to the calendar, it shows you where we are. Okay, so where we are right now is today, it's the 22nd, and we're going to do this today, and then on Wednesday we'll do velocity acceleration, and then finally we're going to wrap up chapter 14 this week. Yay! And then we'll be done. So your exam is going to cover everything in chapter 13 and 14.1 and 14.2. Well, what about the 14.3 and 14.5, that extra little stuff in chapter 14? I'm going to put that in midterm 2, exam 2 later. Don't think that that gives you a free license to take a break and not show up the rest of the class this week. It's not a vacation. I do take attendance, by the way. And a lot of times I find that, students aren't really there, even though they look like they're on the Zoom call. I figure this out by either the usage report, which shows up, which says how many minutes you're on the call, as well as if you respond to me asking you a question or taking a poll. So that's still key. And then you have an exam next week. Okay, so you got the exam. Any questions on how we're rolling? Spring break can't come too soon, I know, but it's not here yet. So there you go. All right, so let's do a couple easy problems and then we'll kick it up a notch. So check out letter A. It's pretty easy. They're saying, hey, integrate this vector valued function. Fine. And so if you do each of them individually, and then you'll put it all together in a component form, the integral of t, come on, that's so easy. T squared over 2 plus some constant, C1. The integral of 3, easy peasy, 3t plus some other constant, C2. And the integral of sine of 2t. And you have to be careful here because you're going to use the sine rule, which says sine u du is going to be negative cos u. And anytime you're doing u sub in my class, I will dock you points unless you show me the u and the du. Well, I do that in my head. Nice, write it down. So here your u is going to be 2t and your du is 2 dt. And I need a 2. I don't solve for dt. That's not how I roll. I go by what's missing. I put a 2 in there, provided I divide out by a 2. And then the intermediate step looks like 1/2 sine u du. And so my antiderivative will be negative 1/2 cos u plus C3. And then I back substitute for the u, which was 2t. So my final answer for this problem is going to be that the integral of r of t is going to be a vector valued function that's going to look like this: t squared over 2 plus C1, comma, 3t plus C2, comma, negative 1/2 cos 2t plus C3. That's my preferred way of showing it. If you want to show me a different way where you pull the C1, C2, and C3 out, I'll do an intermediate step here. Like so. This is what's called a constant vector. This second vector here is a constant vector because it's a vector of constants, essentially. And so if you want, and my math lab lets you do this on some occasions, although I wouldn't do it all the time because I'm going to give you problems where that's a bad idea to like just group them into one big old constant. You'll thank me later for telling you to do it this way. So I'm just going to tell you Rasky prefers this way, but this is also okay. Okay, so there is your first example of actually integrating a vector valued function, and you get a vector valued function. Any questions on that? Is everybody okay with this?
Yes.
Yeah.
Certainly.
Okay, well, we'll find out. All right, so the next problem is a definite integral. And so definite integrals, as you know, have limits on the integral symbol. Some people call them the bounds. I like to call them the limits. Okay, so what I do is, again, I do everything separately. It just makes for easy, and it's easier to read. So somebody says, okay, integrate cube root of t, like that, going from 0 to 1. I always like to rewrite my radicals with rational exponents. So t to the 1/3 using the power rule is going to be what? T to the 1/3 plus 1, divide out by 1/3 plus 1, and evaluate between 0 and 1. I'm going to clean this up. I think 1/3 plus 1 is what? 4/3. And dividing out by 4/3 is the same as multiplying by the reciprocal. And I'll just evaluate that puppy between 0 and 1. And I'll get 3/4, 1 to the 4/3 minus 0, and that's just going to be 3/4. So I got that one done. How about the integral of 1 over t plus 1? That's going to be the log rule. And I want you to use your u sub. U is t plus 1. Du is simply 1 dt, so we're not missing anything. So this looks like the integral of 1 over u du. Antiderivative is ln of u. Back substitute ln absolute value of t plus 1. And you'll evaluate that guy between 0 and 1. So you're going to get ln of 1 plus 1 minus ln of 1 plus 0. Now, ln of 1 plus 0 is ln of 1, which is a nice number. What is ln of 1? Anybody know?
0.
Yeah, 0. Okay, so this result is just ln of 2. Okay, easy peasy. Now what? The final component is the integral of e to the negative 3t, and you're going to use the exponential rule, which, oops, I cannot spell, which says the integral of e to the u du is e to the u plus c. So you are going to need u sub. So I want to see it. Negative 3t is your u, and the negative 3 dt is your du. So I need a negative 3 to even keep going to do the rest of this problem, since that's missing. And what I do is I put the negative 3 in, and I also divide out by negative 3, basically the same as multiplying by its reciprocal. Now this guy looks like negative 1/3 e to the u du, which is going to be negative 1/3 e to the u. And then when I put my u back in, which is negative 3t, then I can evaluate this guy between 0 and 1. So I'll keep the multiple out. And be careful, because e to the 0 is not 0. What is e to the 0?
1.
And by the way, even though I really hate negative exponents, and I will dock you points for not rewriting some final answer with positive exponents, I don't need you to do that for exponentials. When an exponential like e to the something is being raised to a negative, you can leave it alone. Well, what does make you want? Well, like if you had x to the negative 3, I would want you to rewrite it as 1 over x to the positive 3. Okay, just so you know when I like the positive exponents. Okay, so now what's your final answer for letter B? It's going to be a vector valued function, and it's going to be one that has 3/4, comma, ln2, comma, negative 1/3 e to the negative 3 plus, I just distributed my negative 3. So there's your constant vector. Okay. So when you do a definite integral, you get a constant vector as your answer. Okay, so for example 7, I'm going to have you guys try it. I'm going to put you in breakout rooms and have you rock, okay? So let me just tee it up. They're giving you r prime, so they're giving you the derivative of a vector valued function. So you and a buddy need to go find r, but this is what we call initial value problem, because it's got an initial condition that says r evaluated at 0 is the vector with 1, -2, and 3 as components. So you and a buddy are going to have to recover r of t. So I'm going to give you a hint. You're going to start off by integrating r prime in order to find r. Whoops. You're going to integrate r prime to find r. And then after you do that, you'll use the initial condition in order to help you find the constants of integration, okay, to get your final answer. So this is a pretty easy problem. I don't expect you to get too stuck. But if you do, I'll be tooling around the breakout rooms to help you out. So please turn your mic on right now. I encourage you to do that. And then when I open up the breakout rooms, I want you to be able to share and collaborate with your buddy. Okay, so let me go do that right now. Get some breakout rooms up there. Boop, doo, doo, doo. Create rooms, yay. And I'm going to open all the rooms. So go into your breakout room and work with your buddy. Have fun. Okay, welcome back, everybody. How'd we do?
Good.
Good.
Good, good.
I mean, do you feel like you got this, or do you feel still a little confused?
That made sense.
Make sense?
Yeah.
Okay. Let's take a poll. Do you know what fooning is? Nope. Yes, or I have fooned. The vote is going right now, so please take a moment and vote. Okay. You know, when I saw this, I was like, I don't know what fooning is either. And I had to go look it up. So if you don't know, don't worry about it. I'll show you a picture of it. We'll Google it up in a second. Oh, there's two people who, oh my goodness. That just cracks me up. Okay, did everybody vote? We got one person who's not hitting it here. Mm-hmm. Okay, let me show you the results here. It's hilarious. Okay, so it looks like a couple of people have fooned. All right, does anybody want to cop to fooning here? Whoever voted, you don't have to. You can stay anonymous if you want. You want to tell us what it is? They're not saying. They're not.
Is it running?
Fooning. Do you know what fooning is? Not phoning. That's a different deal. This phoning is not fooning. What is, whoops, fooning? I'm not making this up. You guys think I'm just joking. Okay. So let's just look at people who are fooning. Here's what it is. Okay. Goodbye planking. Hello fooning. See this guy right here? That's fooning. Here's some other images of people fooning. Okay. Hilarious. Okay, that is our comedy relief for the day, people. Okay.
So it's just a pose?
Yeah, it looks that way. Yeah. So, you know, if you have an Instagram account, why don't you foon and post it today? Okay. Don't ask me to do it because I don't do Instagram. Okay. I try to stay off of social media. Okay, so let's take a look at this problem. So the first thing that you should have done is individually tried to integrate the components, okay? And hopefully you notice that this is the arctan rule. You should know your arctan rule because I'm really into it. You know, where U is T, du is 1, dt, and A is 1. So your result here is 1 over A, but that's 1 over 1, which is 1. Arctan of U over A, T over 1 is just T, plus C1. Then when you integrate the second component, that's pretty easy, right? Well, what's the integral of sine? It's negative cos, but we have a negative here. So that's going to make it a positive 2 cos t plus C2. And then the last guy, cos 3t, you're going to use U sub here. You're going to need a 3 provided you multiply by the reciprocal. And then you'll get a sign, not negative, and then put your U back in. Okay, that would be 3t. Okay, so what do you have as your answer so far? This isn't the final answer, but I would give you some partial credit if I saw this on your paper. Arctan t plus C1 is the first component, 2 cos t plus C2 is the second component, and 1/3 sine 3t plus C3 is the third component. So you get partial credit for that. Now what? They gave you an initial condition, and this is similar to finding a particular solution when you take Calc 1 or Calc 2. So they're telling you that R evaluated at 0 is this constant vector. How do you use that to help you get the C1, the C2, and the C3? Because that's what you're going to do. Well, when you plug in t equals 0 here, you'll get arctan of 0 plus C1, comma, 2 cos of 0, that's a 0, plus C2, and then 1/3 sine of 3 times 0 is 0 plus C3. That has to equal this vector, 1, -2, 3. And then you just use equality of vectors, which we discussed in week 1 of the course. And for these two vectors to be equal, their components must match. So that means arctan 0 plus C1 has to equal 1, and 2 cos 0 plus C2 had better equal -2, and 1/3 sine of 0 had better plus C3 had better equal 3. That's all. And now you can get your C1, C2, and C3. Does anybody know what arctan of 0 is?
0.
So 0 plus C1 is equal to 1. So that means we got our C1. Check. What about cosine 0? What's that equal to?
1.
So 2 times 1 plus C2 has to be equal to -2. If I subtract 2 from both sides, I get C2 is equal to -4. Check. I got another one. And sine of 0 is just 0. So 0 plus C3 equals 3 means C3 equals 3. Is that our final answer? No, it is not. You have to give me your final answer. The final answer is R of t is now complete. You have arctan t plus the C1 that you got, which is 1. Then your second component was 2 cos t, but your C2 was -4 here, so you're going to do -4. And then your third component, which was 1/3 sine of 3t plus the constant C3, and there's your final answer. So you got it. Did anybody and their buddy end up getting something like this, I hope? I'll check.
Yes.
Yeah.
Kinda.
All right, fantastic. Congratulations. Yay, success. Okay, if you didn't get it, did you at least learn something? I hope. Or maybe it was a good review for you. I don't know. I'm just saying. Speaking of review, I'm going to finish the day with, well, you know, with this hellacious problem here, but it's good review because I need you to know how to do difficult integrations in this course. Because hey, you're Calc 1 and Calc 2 grads, and you know how to do this kind of integration. All of these guys here. Well, this is Calc 2. This one's Calc 1 actually, and this one's Calc 2. So these are all review. So I think it's good for you to take a look at this. All right. So here we go. We're going to do each individually. So there's a hint. I'm going to need integration by parts and polynomial long division. Oh my goodness, help. So do any of those come into play for this first problem we're looking at right now?
Integration by parts.
Yes, IBP is definitely needed for this first one. So just as a review, if you recall, when you're given an integral that looks like a product, which this does, and you don't know how to integrate it using any other regular technique like power rule or exponential rule, then you can use integration by parts and hope that after you identify the u, the du, the v, and the dv, you break it out into uv minus the integral of v du. And the hope is, see, this is not integrable, your original one. And you always hope that the one, when you break it all out using your formula here, that this is integrable. That's the hope.
I do have a question here.
Yeah.
So like if do you want us to use this method entirely if it's like even if the problem is extremely huge, or could we use the tabular method?
I prefer you not use the tabular method in my class. And you probably won't need to because I usually don't give
Them that big?
I don't give repeated integration by parts typically.
Okay.
So
Okay.
please refrain from the tabular method in this class. And that's not asking a lot. But I do
No.
want you to identify everything. You have to tell me the u. You have to tell me the dv. And then you have to get the du and you have to get the v after you identify the u and the dv for me. Otherwise, you will not receive full credit. It's a reasonable request. So for this problem, should the factor t or the exponential e to the -5t be the u?
That would be the t.
Good. So then du is just going to be 1 dt, right? So the dv is going to be the rest of the integrand, e to the negative 5t dt. And let me ask you this, is this true or not?
No.
Correct. It is not okay. Why is that wrong? And yet I see Calculus 3 students doing this all the time. And then when that happens, I don't even grade the rest of your problem, to be honest. I just give you a 0 because I'm so mad at you.
Because
Why is that wrong? What did the person do by accident?
he didn't do it right.
They did derivative.
They took a derivative, not an integral. Good. So when you're getting the v, be sure that you're integrating the dv. And so here, when you're doing the integration of this exponential, you're going to use u sub, and this is going to end up being negative 1/5 e to the negative 5t. Remember?
Yeah.
So now you can break it out into uv minus the integral of v du. So you're going to go u, which is t for us. I'll just write it all out right now, times v minus the integral of v du, but du is just 1 dt. Like that. So the thing that I recommend you do, if you have any constant multiples inside of your integrand, bring it out, clean this up, the first term, by putting the coefficients in front. And then this is going to end up being a minus minus, which is plus the integral 1/5 times the integral e to the negative 5t dt. But we already did this when we were doing the integral of the dv. So good news, you don't have to, do over, but you do have to be worried about your constant of integration. And you may want to clean this up because that is a negative 1/25. Okay, so let's save that for later and keep going with this integration problem. Oh my God, now what? Number 2, the second component, yuck. So we're going to try and integrate 3t over the quantity 2 minus t squared squared. 2 minus t squared squared. Okay, this is actually a Calc 1 problem. It's the power rule. It's basically going to end up looking like 1 over u squared du. But first, tell me the u and the du. Otherwise, I can't give you full credit. I do like you to identify those. I know if you do them in your head, like, oh, I always do them fine in my head. No, you don't, because I don't. Sometimes you get, get a bite in the rear end when you forget a negative. So it could happen. So the u is the 2 minus t squared for this problem. And then du is the derivative of 2 minus t squared, which I believe is negative 2t dt. Good news and bad news. Good news, the t and the dt already exist in the integrand, but we need a negative 2. No problem. I'm going to put one in, provided I divide one out. And this 3 I'm going to pull out in front. So now my intermediate step is the following. I have negative 3/2 times the integral of 1 over u squared du. And I'm going to rewrite this as the integral of u to the negative 2 so I can use my power rule. And so then I'll have u to the negative 1 divide out by negative 1. Of course, I'm going to have a C2 here. I've got to have my constant of integration. A negative times a negative is a positive. And when I rewrite this with positive exponents, I get that. And then finally, put your u back in. What was it?
Two minus t squared.
And do not distribute the 2 over parentheses. Just leave it. Okay, save this for later. And then the last integration is going to be, a real doozy. Yeah, polynomial long division. Do you even remember how to do this? I hope so.
Yes.
So if you're integrating what's known as an improper rational function, and this is an improper rational function. What? It's improper? Yeah. It's a rational function because it's a polynomial divided by a polynomial. And then it's an improper rational function because if the degree of the numerator is greater than or equal to the degree of the denominator, it's considered improper. And anytime you have an improper rational function, you've got to do polynomial long division. before you can integrate. Like, don't try to integrate that. So yikes. So then what? Well, you're asking how many times does t squared plus 4 go into the dividend t squared plus 3t. So only focus your eyeballs on the highest power terms to make it easier for yourself when you do a polynomial long division problem. That way you'll stay out of too much trouble. So the question is, t squared times what would give you t squared? This is not a trick question. What would I need to multiply by?
1.
1. Okay, so we start off our quotient up top there with a 1, and then you multiply this 1 with the entire divisor. So you're going to have t squared plus 4. But this is bad because you don't want to vertically align unlike terms. I mean, what do you mean? Because you're going to subtract them in a moment. Oops. So what you should do is put the 4 over there to the side, because you can think of the constant term for the dividend to be 0. So you can put that in as a placeholder. And that's what I do, just to sort of keep things even. So then what? I'm having trouble with my erase tool. It does all kinds of wacky stuff. Crazy. So you're going to subtract. So be careful, because you want to distribute that negative. So t squared minus t squared is 0. 3t minus nothing is still 3t. And then 0 take away 4 is negative 4. Am I done, or should I keep going with this polynomial long division? And how do you know when you're done with polynomial long division?
You're done because nothing times t squared could get you 3t.
Yeah, well, without having to do a fraction. So this degree is degree 1, which is less than the degree of the divisor. So you're done. And this is your remainder. This right here is your quotient. And this guy up here, which looks like he erased, this is your divisor. And what I want you to do after you get done doing a polynomial long division, when you rewrite it, you want to rewrite it as your quotient, which for us is a 1. That's a 1 up there. 1 plus the remainder divided by the divisor. This is what you're now going to integrate. Okay, I got good news and bad news. The good news is 1 is really easy to integrate with respect to t. It's just t. Plus this beast right here, I wouldn't try to integrate that right now. You're going to get into a world of hurt. What you're going to do first is do what I call the split up trick, which isn't really a trick, but my Math 45 students think it is. So basically it's just taking a fraction and rewriting it as the sum of 2 fractions. Okay, so what do I mean? You're going to integrate the first guy, 3t over t squared plus 4, minus the integral of 4 over t squared plus 4. And both of these integrals have very different techniques. And yet I get students who make it to Calc 3 and they still don't know the difference. And that is concerning. Hopefully not present company. This one is going to involve the log rule. What's the log rule? 1 over u du is ln of u plus some constant. So you do need to identify the u and the du in my, on your handwritten work. This 3, you can pull it out front, but the u is the entire denominator and du is 2t dt. So t and dt are already in the integrand. That's good news. What am I missing? Well, I need a 2. Put 1 in, and provided you multiply the front of the integral by its reciprocal. So right now, once you pull out the 3 also, you have this, and then using your log rule, you're going to get this, right? And we'll put a constant, but it's going to be C3, but we'll kind of save it for later. Now this guy, anybody know how to integrate this? Not the log rule.
Arctan.
Arctan, good. This is the arctan rule. So if you're doing an arctan or an arcsine, I want you to tell me the u, the du, and the a to get full credit. U is just t, du is 1 dt, a is 2. So your antiderivative will be 1 over a, arctan of u over a plus a constant. We'll just combine these into one big old constant, which is 2. Oops. Come on, baby. Nope. So, sorry, my Surface Pro got stuck in a weird loop. So you've got the arctan rule happening there. So this is a 2. Sorry. So now what? So when you put it all together, this last component, his antiderivative, which is pretty hellacious, I know, but I was trying to make a point by making it that hard. And then lastly, for some reason, my math lab gets a little grouchy if you use arctan. I guess it prefers tan inverse, which is the same thing. And then you can combine your C3. So what's your final answer? Oh my goodness. Your final answer is going to be this ginormous vector valued function. So we got negative a fifth t e to the negative 5t minus 1/25 e to the negative 5t plus c1, comma. Second component was 3/2, the quantity 2 minus t squared plus constant of integration c2, comma. And by the way, if you don't distinguish your c's, like you just put plus c plus c plus c everywhere, every time you do that, I'm going to take away a point. I want to see the c1. I want to see a c2. And then this last guy right here goes in the last slot here, t plus 3/2 ln t squared plus 4 minus 2 arctan t/2 plus C3 is your final answer. I know that was pretty bad, but hopefully the review of integration techniques was well worth it. Okay, so I'm done with today's lecture. If you want to stay and ask some last minute questions, you're welcome.